know that this process can simplify. So what I do, I start with this. I say when we apply force here, I know I make a little animation that I know that this goes down like that, and also the force here, which is half of this speed, is going to cause this to compress, and then this strap going down, and this two are going to compress. So all sort of things happen. So, but I know that this unit is got this exactly the same thing on the right, and it's symmetric. So if I find that the spring constant equal to this, so if I combine all this together and put just one spring here, then I have exactly the same spring on the right, and then I have two springs connected in parallel, right? Then I can have that and consider this spring put together, and finally at the end, I want to find the spring constant for the system starting from the top all the way to the bottom, the entire thing. That's what I try to find, right? So before I actually put the number in the calculator, I make some little drawing. I say, okay, this one is already K1, right? Right here. And also K1 is given. What is the value of K1? Is 3. And this, then, let's do the data quality here. This is this there. And then this also, this acts like a spring, this part. Going to compress, right? When it's linear elastic, when you have permanent deformation, no. But when it's linear elastic, it's going to act like a bar. Now the question is, what is the spring constant for this bar? To answer that question, you come with this formula and say, I have this formula. This formula is given to me. So in order to find the spring constant equal to that, what should I do? I should compare it with F is equal to K times delta X. Right? The formula we had in high school. F is force is equal to K times the spring constant times deformation, delta X, right? So how can I rewrite this formula in the form of F is equal to K delta of force, here force is equal to the spring constant times delta. Well, it's extremely easy. Just multiply both sides by AE divided by L. So you get AE over L times delta is equal to P. So P is equal to AE over L times delta. So what's the spring constant? AE over L. It's just very easy, right? So whenever you want to find the spring constant for whatever, like for this, you got to write that formula in form of force is equal to spring constant times deflection. Whatever that thing is your spring constant, right? So here I write it for another spring. I can make another, instead of bar, I convert it to another spring. And the spring constant is, let's call it K bar 1, because we already have K1. So I use another symbol. But I don't want to use another K like an M, because this K is spring constant. So I put a bar here. So that distinguishes this from K1. So I say K bar 1. You can call it whatever you want, right? It's just a matter of preference. So K1 bar is equal to, what should I put? A1 E1 over L1. Now you come to this table. A1 is given, which is 1. E1 is also 1. L1 also I said, take it 1. Right? Don't put it in the calculator. Continue making your drawings. So you're going to have another spring here. And this is K bar 2. But by the same token, you have A2, E2 over L2. Now you go to the table. A2 is equal to half. E2, 1. L2 is also, you take it 1. Right? So you replace that with a spring. This is already a spring. So you just put it right here. K2. And the value should be given in the table. K2 is equal to 1. Now, you go ahead and replace this guy is the spring, right? So you get another spring here. Let's call it K bar 3. So this is 3, and it's not the spring, you just call it K bar, right? Is equal to A3, E3 over L3. You go to the table, A3 is 2, E3 is 1, L3 also is taking 1, if I'm not giving it. Yeah, you take it just 1. So I got rid of this, now you go to, yeah.
You said it was 2, but you wrote 3.
Here is 2.
No, you wrote 3. So for K3,
Yeah, it's A3, E3 over L3. A3, according to the table, is 2. It is, A3 is 2. Yeah, this is yeah. Sorry. Yeah, sometimes, you know, you actually, I see it, but I don't, obviously, it's my fault. It's my fault. Yeah, so 2 times, no, it's not too early. It's actually, I had very good sleep last time. I slept around like 8:30 p.m. for the first time in my life. I usually sleep at 2 or 3 a.m. in the morning. And I woke up at 5, and this was the first time in my entire life that I didn't use the clock. Because I have a big clock, and I have a hammer too. But this time I just woke up on my own, and nobody helped me, and I was so proud of myself. I finally made it. Morning man. But what I was doing here was, okay, A3, which is 2 times E3, which is 1 times divided by L, and it's 1, so we got rid of this guy too. Now we go to K3. K3 is already given to you. Is 2. And now, this is an interesting thing. We also have a deformation come from the beam. So between the point C and this part, we have a spring that is equal to the flexure of this beam. So how can I find the spring constant? Again, you go back to this formula, and you say, I've got to rewrite this formula as is equal to force is equal to something times deformation. That something is by the K. So if I write that, my K would be 48 EI divided by L cubed times delta. Right? So force is equal to 48 EI divided by L cubed times delta. So this guy is my spring constant. 48 EI divided by the length of beam to the cube. So here I put another, before I do that, there is another spring here, which is exactly the same thing. You see, this guy and this guy are the same. Right? And then you have here a spring from the beam, K beam, which is 48 times E of beam, which is 1, times I of beam over the length of beam. And if I'm not, if I do, let's just take it 1, the length of beam, take it 1 to the cube. Right? So that's the entire thing you have. Right? And this is the final point C that I put a fourth P here. Right? So let's go ahead and simplify. So here, yeah. Third question? So let's go ahead and simplify. So what do I get from these two guys? They are in parallel. You see that? Because we assume that plate, the rigid slab, is not going to deflect like angular deflection. It's going to perfectly go down or up because of these constants. You see these constants? So it's kind of assumption in the actual physics, it may get a little bit slow, right? So this is going to be 3, so you just add it, you come to this formula. Look, you don't need to memorize anything. Everything like this is going to be given in the exam. So you just say, the corresponding, the string constant is just sum of whatever you have in parallel. So 3 plus 1 is 4. So here, you're going to have 4. What about here? 1.5. What about, so here we can say, because this is in series, this is in series, this is in series, this is in series. Now, if you want to simplify this, then, in fact, you have a spring here, A3, which is 2, and then another one, which is 2, and then another one corresponding to this guy, which is 1.5, and another one, which is 4, right here. So what is this particular configuration? They are in, you come into see, they are in series. One end of the other is connected to the end of the other one. So if I have in series, then 1 over k total, if I replace this with just one spring, say k total, 1 over k total is equal to 1 over 2 plus 1 over 2 plus 1 over 1.5 plus 1 over 4. Then you find k total is equal to the calculator. Don't forget to invert it. Very good. 0.5217. All right, so that's the spring you put here. Now, let's go ahead to the next level of simplification. The next level of simplification is now consider this is that, right? You have 1k total here, which is 0.5217. Another one, exactly the same on the right, 0.5217. And another one here, which is beam, K beam, and is equal to 48. Right? And this is the final point C. Now what should I do? This is the ground, and this is point C. I need to replace these guys with just one spring constant. Before that, what can I do with these two guys? Add them together. So if I add them together, finally I can write 48 right here, and this is going to be twice of 0.5217. And this is fourth P at this point C. This is a more simplified version, right? Now finally, these are in series now. So what do? I say 1 over k total, which I just call it k. This is the real total equivalent to the entire thing, right? Between point C and ground, the entire system. So 1 over k is equal to 1 over the spring constant of the first one, 48 plus 1 over spring constant of the second one, 0.5217. Now, put it in the calculator. I don't want this to dry. So, there you go. the finally, the spring constant K becomes 1.021. That means that you can get rid of the entire thing, everything here, and replace it with just one spring K is equal to 1.021. Now, I have this problem. At the end, when you simplify, you have a force P here at point C, and you have one spring, the spring constant is 1.021, and this is the ground. Now, what's the deflection of this point?
E divided by the 1.
There. This formula. So the deflection is whatever force divided by the spring constant. So the deflection delta at point C is force divided by 1.021. I saw several successful solutions. The final result 1.021. That's the number that I was expecting.